The topic of this screencast is the facts of evolution. I will be focusing on the paleontological evidence. Before talking about evidence, we need to understand a few basic ideas. The first is biological evolution, which states that a species undergoes genetic change over time. This usually occurs through natural selection, which says that an individual with helpful genes is more likely to reproduce and pass on those genes. Over time, this can result in a new species. Second thing you need to know is that paleontology is the study of past life forms by the examination of fossils preserved in rocks. The total number of species that have ever lived on Earth is estimated at as many as 4 billion species. But we have only discovered about 250,000 fossil species. That's only between 0.1 and 1% of all of the species that have ever lived. To understand why fossils are so rare, we have to look at how fossils form. The first, most obvious step is that an organism must die. This usually needs to occur in an aquatic or at least partially aquatic area. The second step is that the carcass must be covered with sediment or debris. The anoxic conditions are best at this stage. Next, there needs to be a leaching of the organic molecules of the organism. So all the organic molecules need to be pulled out. Then these organics are replaced with mineral salts, most commonly calcium, magnesium, phosphorus, potassium, and silicon. After the fossil is formed, erosion must then expose the fossil, or it has to be dug up if you know roughly the area the fossil should be. Then the fossil must be found, and this is very time sensitive because it has to be found before erosion and other natural forces completely destroy the fossil. An important tool for paleontologists is radiometric dating. This is where you date rock layers based on the presence of certain radioisotopes. And to do this, you find the difference between the amount of isotope that is present and the decay products that are present. Each isotope decays at a constant rate that differs from all other isotopes. This decay rate is called the half-life because it is the time that it takes for half the isotope to disappear. And the only reason that radiometric dating works is because rates are not affected by external forces. That means you can change the temperature, the pressure, or any other factor, and the half-life remains the same. Radiometric dating is important when looking at fossil distribution. By dating a certain rock layer, you can also determine the age of all the fossils within that rock layer. It's also important to note that the fossil distribution is linear. It's not cyclical or random. And this linear trend goes from deep to shallow, usually simple to complex, and ancient to more recent. What this means is you won't find this recent fossil here in the same layer as this much more ancient fossil here. All it would take to disprove current evolutionary theory is to find a horse fossil in the same rock layer with a dinosaur fossil. or a modern bird fossil in the same rock layer as an ancient extinct fish fossil. If evolutionary theory is correct, we would expect to find a gradual change within the lineage of a species. So we should find intermediates between the ancestor and the more recent descendants. Several of these intermediates have been found, and they are called transitional forms, which are fossils that span the gap between two very different kinds of living organisms. So you can find transitional forms between jawed fish and amphibians, or reptiles and birds, or land mammals and whales, just to name a few examples. We can start by looking at amphibian evolution. On top you'll see an ancient lungfish. This fish had lobed fins, it was fully aquatic, and no neck. You'll also notice that it has a round head with the eyes on top. On bottom you can see one of the earliest tetrapods. This is a vertebrate with 4 limbs. It has a very flat head with eyes on top, which is very amphibian-like, and 4 limbs adapted for walking on land, but it was still at least partially aquatic, just like modern amphibians. In the middle you can see the amphibian-like transitional form, Tiktaalik. It has a flat head with eyes on top, just like the tetrapod, and it also has a neck, unlike the fish. But other than those, it still has mostly fish-like characteristics. Its fins, however, are more sturdy than its ancestors, so it can lift itself up off the ground and stick its head above the surface of the water. And Tiktaalik could breathe above the water when it stuck its head out because it had both lungs and gills. Now I'd like to show you a video on a transitional form called Ichthyostega.
It almost looks like Tiktaalik, but Tiktaalik is long extinct. In fact, this is one of Tiktaalik's descendants, a critical link to the evolution of humankind, the 5-foot-long Ichthyostega.
Ichthyostega is very interesting in the sense that this animal represents one of the first documented cases in the fossil record where we have a vertebrate with recognizable digits in its limbs. The hand of Ichthyostega is not known, but the hind limbs are very well known. And interestingly, there's not 5 digits, but there are 7.
Its ancestor Tiktaalik used both gills and lungs for respiration. Ichthyostega only uses lungs. A sturdier ribcage supports his body when out of water, relieving pressure on the lungs. That means Ichthyostega can draw much deeper breaths than Tiktaalik. Like a modern-day whale or dolphin, it gulps air at the surface before launching its attack.
If you think about it, in a very tangled swamp where you have a lot of vegetation material down and sticks, legs are really useful. You can pull yourself through branches and dead leaves and material. They're very useful for underwater appendages.
But Ichthyostega is as comfortable out of water as he is in it.
But Ichthyostega certainly could get out. Whether it could lift itself off its belly, there's a big debate about this. How strong were the shoulder girdles? How strong were the forelegs? But it is the ancestor that does give rise to animals that could hold themselves up, these first true amphibians.
Next, I'd like to talk about the evolution of birds. The most commonly accepted theory is that modern birds evolved from feathered theropod dinosaurs, like this first picture shown. These dinosaurs had short front appendages, and they were very reptilian but still had some bird-like qualities. In the middle is Archaeopteryx, one of the most famous transitional forms. It was still very reptilian but did have a few bird-like qualities, including this wing-like appendage, an opposable first digit, and it was also covered in flight feathers that are similar to modern birds, so it was most likely able to fly rather than just glide. Archaeopteryx isn't the only transitional form between theropods and birds that has been found. Sinorthosaurus is an even more ancient ancestor or relative of modern birds. It was completely covered in filament-like feathers that were completely useless for flying, but may have served a purpose in keeping it warm. You can see these feathers in the fossil here and all over the rest of its body in various places. Another interesting transitional form is the Microraptor. It's called the four-winged theropod because it has 4 separate sets of flight feathers. It could most likely at least glide, if not fly. Now I'd like to talk about the evolution of whales from land tetrapods. Pachycetus, shown on top, was terrestrial, which means that it lived mostly on land. It is an ancestor or common relative to modern whales. It doesn't look like a whale, but it did have whale-like ears and very simple teeth. The next transitional form, Rhodocetus, was a mostly aquatic species. It still had 4 distinct limbs, but its nostrils were shifted slightly backwards, and it had these extensions for muscle attachment that would make it a very strong swimmer. A more recent transitional form is the Dorudon. It was fully aquatic, and as you can see, its hind limbs are no longer attached to the rest of the body, and they are much smaller, as are the front limbs. The nostrils were shifted far enough back they are considered a blowhole. On the bottom is a modern baleen whale. It also has a reduced hind limb that's detached from the rest of the body. This is considered a vestigial structure, meaning that it no longer has the same function it had in its ancestor. Finally, I'd like to show one more example of change within a lineage. This is easily shown through the evolution of a horse limb. You can see that over time, the size generally increased. You can also see that the number of toes decreased over time. 55 million years ago, ancient descendant of modern horses had 4 toes. Then 20 million years later, the number was reduced to just 3 toes, and so on until modern horses have only 1 toe. But these toes didn't just disappear. They were adapted to what's now known as splint bones. These splint bones are vestigial structures because they no longer act as toes like they did in the ancestor, but they do support and brace the horse's knee. This is just a small sampling of the paleontological evidence that supports evolution, and there is still more evidence in other fields of science. But I hope this has at least given you a basic understanding of why evolution is true.